All right, well, let's go ahead and talk through this one, kind of get back into it. Then we're going to talk about the quiz from right before break. And then I'll kind of give you a heads up on what's coming. Just as a reminder before break, we talked about angles in quadrilaterals. Well, actually in all polygons. So interior angle sums and exterior angle sums. So we had 4 different formulas for that. In fact, let's look at a quick review of those things as I talk through them. So we had interior angle sums. Remember we split it up into triangles, and we could always draw 2 less than the number of sides triangle. So if we had like 10 sides, 10 minus 2 would be 8 triangles times 180. And then if we wanted each interior angle, if it was regular, we had to divide and split it equally among all 8 angles, or 10 angles in that case. And then exterior angle sums always added up to 360, no matter what polygon we were talking about. And if it was regular, we could split it up evenly, just dividing by how many sides there are. We saw problems that involved more algebra, like these kind. And in that case, we just found the total. So this was a hexagon. So we plugged in 6, found the total should be 720, and then just added all those angles up to find x. So that was a different version of what we studied. And then we talked about trapezoids and kites. And let me put this up here. So we had started our... This document is going to be really full of information. We've started it. So kite properties and trapezoid properties. And we had a specific trapezoid kite called an isosceles trapezoid, where there was some additional information. So probably over break, that stuff, I'm guessing, kind of just drifted off. So maybe over the next few days, be reviewing your sheet. I'll do a quick reminder right now. So remember, in a kite, the definition is a quadrilateral with 2 pairs of consecutive sides that are congruent. Opposite sides are not. So we see 2 tick marks versus 3 on opposite sides, but the ones that are together or next to each other are congruent. So then we also had perpendicular diagonals, 90 degrees. We had the long diagonal bisecting, so this long diagonal bisecting the short one to split it into 2 equal parts. And then also the long diagonal bisects these 2 angles. And then these 2 angles on the short diagonal are congruent. So that was the kite properties. And a lot of our solving with that was either triangle angle sums, like I give you maybe this angle and ask you for this angle. And you know that this angle and that one's 90, and then you use that they add up to 180 and solve for x. And then the other version was using the fact that we have the right triangles and use the Pythagorean theorem to solve. So quick reminder on that was one like this problem. So we were told it's a kite, and we know that's a right angle, and then we were given these different lengths. To solve for x, we had to plug it into the Pythagorean theorem. And remember, when you square something like 2x minus 2, it's really that thing times itself, and that creates a trinomial, meaning 3 terms, not just 2. And then we solve, in that case, we solved using the star. So that was a typical looking problem for a kite. I'll come back to that in a second. Trapezoids, definition there. It had exactly 1 pair of opposite sides that are parallel. We call those the bases, and then the other 2 sides that aren't parallel are the legs. And in just a regular trapezoid, the same side base angles are supplementary. They add to 180 because of those parallel lines. And if we had looked at this 2 units ago, we would have called those same side interior angles, SSIAP stuff. Anyway, and then we had the isosceles. Now we had the same thing, the same definition, etc. of a trapezoid, but now we have 2 legs that are congruent. Because of that, we had the 2 base angles, the 2 pairs that are congruent. And that allowed us to solve also for angles, etc. We also added that the diagonals are congruent in that kind of trapezoid. And then the last two things we talked about was this mid-segment theorem, where if we are told that this pink line in this case, if we know that's the mid-segment, meaning it's going through the two midpoints, and we're shown that by the congruent marks, then it is half of the two bases added together. So base 1 plus base 2 divided by 2. And that looks similar to the area of a trapezoid, only we just add the height in front, so h times. And that kind of gets us caught up. Here's an example problem that we did, actually a couple, where we used that mid-segment. Remember to always write both sides of any formula. That way, if I tell you what the mid-segment is or give you an expression like this example, you can plug it in on that side. So we got rid of the 2 in the denominator by multiplying both sides and solved pretty straightforward from there. And then our area of a trapezoid problem was a little bit more involved. We had to know that this 10 could be copied straight down and then splits that other base into 2 equal parts on the ends. So that left us with taking this 10 away from the 22 and left us with 12 to split evenly, and that left this side being 6. And then we just used the Pythagorean theorem to solve for the height and plugged it in the formula. So lots of various formulas that we had to use. This one obviously is a trapezoid. And if I go label the angles as 105 and 75. Now, we haven't talked about properties of a parallelogram. Like in A, it asks if it's a parallelogram. The picture wouldn't suggest that it is, but we do need to use properties to either say yes or no to that. So I will tell you it's not a parallelogram. We're going to save parallelograms till after Christmas break, actually. So I'll give you, in a second, I'll give you a little bit more about the plan. But is this a trapezoid? Remember, the definition of trapezoid is that it has exactly one pair of opposite sides that are parallel. But this doesn't show anything parallel. But can we prove that something is parallel? How, Parker? Yeah. So for this one, these two angles are supplementary. And so by the, actually, let me write it up here. So by the converse, if you remember this page, I had a bunch of ways to prove things. By the converse of the SS, same side, interior angles postulate, we know that PS is parallel to QR, because those two add up to 180, and they should if those two lines are parallel. So, is it a trapezoid? Yes. Those two lines are parallel. Okay, is PQRS an isosceles trapezoid? How would we be able to tell if it is that or not? Well, remember, isosceles trapezoids have congruent base angles. So we see the bottom two are. Is there a way to prove if S is also 105? I can think of two ways. Yeah, Isaac?
Q are congruent, and you can add a 75 minus 1.
Yeah, good. So we already proved that these two lines are parallel. So he says, what if we do 180 minus 75? Well, that's 105. So now we've proven that these two angles are also congruent. So yeah, it's definitely an isosceles trapezoid as well. Okay, so PQ, is that a side length or an angle or just what is PQ? Yeah, that's a side, right? That's the length PQ, and it is on the left side. Anyway, I'll go fill all these in, but it says what is the length of each side of the quadrilateral. So let's get rid of some of this busyness. So PQ is x, QR 2x minus 1, RS 3x minus 8, SP x plus 1. Okay. What do we do with those side lengths to be able to solve for x? We have 4 different expressions for it. Okay. So since we know it's isosceles, that means we can set the legs equal. It's pretty common to be given more information than we need, or at least looks like it is. So just don't set all of them equal to 180. Don't set like x. Don't set the top PS equal to QR because those are not congruent. All right, how do we solve this?
Minus x plus
I agree. Okay. And so we'll get 8 and 2x, and so x is 4. And then it says find the length of each side, and so we'll just plug 4 in. And for x, so this side will be 7, this side will be 5, this side will be 4. And then here's a good check on our work. If this side happened to not be 4, we would know that we solved incorrectly for x. All right. How'd that go after some days off? Anybody remember all that stuff? Okay. Let's pause here and talk about your Okay, here's where we're headed for the remaining 2 weeks. Like I said, the third week before break is, there we go. The third week before break is finals week, so we'll have, our schedule is Monday, Tuesday our normal, and then Wednesday, Thursday our final schedule. So we'll review those 2 days. And then this Wednesday, so 2 days from now, we do NWEA. So some stuff coming up that will kind of get in the way of our regular flow. But we're postponing the remaining part of the unit. In other words, the rest of all these properties. So all those parallelogram properties, we're going to postpone until after Christmas break. And we're going to start on 2 things. One, parallel and perpendicular lines, which will allow us to do what we call coordinate proofs. Let me show you what a coordinate proof looks like, at least the basic one. And we're not going to obviously start this yet, but we're going to get there this week. So you're given a trapezoid graph on graph paper. That's why we call these coordinate proofs, because each of these points have a coordinate pair. What would be the coordinates of point R right there? Negative 4, 4, okay? So left 4, up 4 would be the coordinates of point R. And then point T right here, what would its coordinates be? Yeah, good, 0 for the y coordinate. How about point P? Yep, negative 6, good. And point A right there. Okay. So we're going to get to this point where I can just give you 4 coordinate pairs, not give you the graph. Like in this one, the graph is provided as well. But if I just gave you the 4 pink points as coordinate pairs and asked you to prove if it's a trapezoid, and if so, is it an isosceles trapezoid? So your job will be to be able to graph it first and then decide, hey, am I looking at a potential kite or a potential trapezoid? And then from there, be able to prove which one it is, okay? These are more algebraic proofs using properties that we wrote down on our properties page rather than the full 2-column statements, reasons kind of proofs, okay? So that's our goal for the next 2 weeks. In order to do that, we need, this is a trapezoid. We're also going to do this with kites, but for a trapezoid, we need to be able to prove if these 2 lines are indeed parallel, and we need to be able to prove that these 2 lines are not parallel. To prove it's a trapezoid, we have to prove there's exactly 1 pair of opposite sides that are parallel. Okay, so we need to be able to prove the 2 pink sides are parallel, the 2 blue sides are not. How do you prove if lines are parallel using coordinates on a graph? So we haven't done this in this class yet. All we've done, if I give you this angle and this angle, we could maybe prove those 2 lines are parallel using converses and that kind of thing like our warm-up did. But we have not done this with more of an algebraic style where we're given coordinate pairs. So what do you remember about parallel and perpendicular lines from algebra? It's probably like a day of algebra a year ago. So if you don't remember, it's not surprising. It's okay. Anybody though? Anybody remember that? Okay. So grab your note packet and let's start putting some of that in here. We might have already. We put some formulas that we need. No, we didn't. Okay. We did write this stuff down. I want you to just, for now at least, just note the slope formulas for a second. We'll come back and do the distance probably tomorrow. So that should be in your notes. If not, we're going to put it in there here in a second. All right. Coordinate proofs. We're going to do these with kites and trapezoids now before Christmas break, and then after we'll learn properties of parallelograms, which includes rectangles, rhombuses, and squares. Then we're going to do it with those as well. So this unit is quite a lot. Okay. Now we have the slope formula written down below. We're going to use it for this a couple times. So parallel lines. If I'm given 2 points on some graph, so let's say given 2 points, here's what we're looking for. Let's make this real big and then we'll come back and talk about steps. parallel lines have the same slope. If you remember the word steepness as kind of a synonym for slope, steepness. If you're hiking on two trails with the same steepness, then you would expect them to look the same, right? Like they're the same steepness going uphill or downhill. Okay. So that's the big idea. So find the slope and see if they're the same. A couple of details with that though. So find the slope of all lines. Let's call them sides instead of lines. And we can put this as a quick reminder, m equals, seriously, quit doing that. M equals y2 minus y1 over x2 minus x1. We'll review what those are in a second. Then you want to make sure you've reduced or simplified all slopes. So if one is, let's do something easy. If one is 2/4 and the other is 1/2, make sure you reduce the 2/4 so you can see that they're the same. The other option is you can make them all decimals. How do you do that? Real quick, don't write this. Just what if I had like 7/13? How would you make that a decimal so you can see if it's the same as another one? Huh? Divide by 10?
Oh, make the fraction decimal?
Yeah.
7 divided by 13.
Yeah, just divide top by bottom. Okay, so let's write that. Divide top by bottom. Okay, and then your last step, obviously, if it's same slope, sides are parallel. Does this ring a bell from Algebra 1 at all? Okay. You can put what I'm about to write right next to this slope note in our parallel line stuff. Or I'm going to make more of a general note down here, and that is, let's go remind everybody what y2 and y1 even means. So just draw a little graph, and let's make sure we label x and y, just to review that. So when we have y2 and y1, what we're talking about is the x and y coordinates of the 2 points. Okay, so it doesn't actually matter which order, like if you call this point 1 or that point 1, it doesn't matter. The thing that matters, actually two things, make sure it's always xy, not xx. And make sure you don't mix, like this is not x1, y2. You can't mix those. The same subscript number has to be with each letter in the same point. So x1 is the x coordinate of the first point, x2 is the x coordinate of the second point, etc. That's all that we're talking about there. Any questions on that? Okay. So we'll start tomorrow with an example and how we can use this to find slope. You can do yourself some good by reviewing those properties of kites and trapezoids. You'll want to be super familiar with those as we get into this more.